In this video, I want to take a look at the problem of knowing how close we want to approximate an integral and figuring out how many subdivisions we need in order to do that. So my first question here then is, suppose I want to know the minimum value of n so that the trapezoid rule approximates this integral right here to within 0.001 of the actual value. Okay. Now, again, I can do this and actually find the actual value because I can do an antiderivative, but I just want to illustrate this process with this problem. Okay. So the thing I know about the error for the trapezoid rule is that it's equal to or less than k times b minus a cubed over 12n squared, where k is an upper bound on the second derivative of the function that I'm integrating. Right? And so what I want to do is I want to make this thing less than that 0.001. Because if I can make this thing less than 0.001, I know the error is less than this thing, so then I'll know that the error is less than 0.001. Okay? So first thing I need to do is to establish what k is. So the function that I'm integrating is, x cubed minus 2x. So the derivative is 3x squared minus 2, and the second derivative is 6x. Okay. The interval that I'm integrating over is 2 to 8. So I'm integrating from 2 to 8, and I want to know what's the maximum value that 6x could be. Well, 6x keeps getting bigger as x gets bigger. So the maximum value is going to happen over here at 8. So k is going to be 6 times 8, which is 48. So the biggest the second derivative could be happens at the end point here. And it's 48. Now, so what I'm going to do is I'm going to plug that in, and then I got to figure out what n is. So I've got 48 times 8 minus 2 cubed, that's b minus a, over 12n squared. We want that to be less than or equal to 0.001. And what I'm going to do now is just solve for n. So multiply both sides by n. I've got, well, the 48 divided by 12, that's actually kind of nice. That's just 4, right? So I've got 4. This is 6 cubed. 4 times 6 cubed on the top. I'm going to multiply by that n squared. So that comes up over here, n squared, and I'll divide by this thing. So over 0.001. I should point out that as you're multiplying and dividing with an equality, it's no problem. With an inequality, you've got to be careful that you don't swap the order of the inequality. But the thing is, both n squared and 0.001 are positive numbers. And if you multiply both sides of an inequality by a positive number, it does not change the direction of the inequality. Right? So this is still a less than or equal to. So n then is just going to be greater than or equal to the square root of whatever this is. 4 times 6 cubed over 0.001. And I'm trying to take out my handy dandy calculator and find that 4 times 6 cubed divided by 0.001 is, take the square root, wow, pretty big. I get 929.5. I'm going to pause for a moment and see if I agree with that. Yeah, I see, I agree with that. So the thing is, though, I can't take 0.5. N has to be an integer. So I've got to take n equal to 930. Right? You always got to go a little bit bigger. So 930 to get an accuracy of 0.001. That's pretty dang many. That's a lot. So let's try it with Simpsons Rule now. The thing that I know with Simpsons Rule is that the error for Simpsons Rule is always less than or equal to k times b minus a to the 5th power over 180 n to the fourth power. And k this time is an upper bound on the fourth derivative. Okay, we want this to be less than 0.001 so that the error will be less than 0.001. So let's get a sense of what k is now. So the function that I'm dealing with is still that x cubed minus 2x squared. No, minus 2x. Let me scroll back up and make sure I've got that right. X cubed minus 2x. That was the function we were dealing with. Okay. So the first derivative is the same as it was before. It's 3x squared minus 2. The second derivative is 6x. The third derivative, that would be 4. So let's try the third derivative, is 6. And the fourth derivative is 0. 0. That's interesting. So k equals 0. And this says that the error by Simpsons rule is less than or equal to 0. So n equals 2. Remember, you got to take an even one. I can't just take 1. I got to take 2. And actually, we saw this integral in a previous. We used Simpsons rule to estimate this in a previous one, and we got it exactly. The thing is, with Simpsons rule error being related to the fourth derivative, if you're estimating a cubic curve, then the fourth derivative is 0. And Simpsons rule will get it right every time. Now, if it's not a cubic curve, then you're going to have some fourth derivative, and you're going to do it just like we did the previous problem here. But I wanted to point this one out, that Simpsons rule is using quadratics to approximate the function. But it turns out that quadratics approximating cubics works exactly. You can't just use any quadratics. Simpsons rule is very specific in that when you split your interval up, you cut it up into equal length pieces. And so the 3 points, you got 3 points here that you're fitting a quadratic through. They're 2 endpoints and the point exactly in the middle. And it turns out with that situation, if you're trying to put a quadratic through the same 3 points that a cubic goes through, and the 3 points, the x values are equally spaced, then the area underneath the cubic and the area underneath the quadratic are exactly the same. Not at all immediately obvious, I don't think, but it's true nonetheless. Okay. So anyway, if you know how accurate you want your estimate to be, then you put that over here. You know what a and b are from your integral. You figure out what k is because you look at your function, you take the fourth derivative and see when that's maximum. So the maximum value of k, the maximum value of the fourth derivative is what turns out to be k, and then solve for n and see what n has to be. Okay. If you're using the trapezoid rule, then k is not related to the fourth derivative, but instead k, like this one, was related to the second derivative. Okay. Anyway, I'll admit to you that this error approximation is not a big part of what we do, but I think it's important enough to spend a couple videos on here, and you should try some problems.